What they see in the lab is not exactly what they can show other people. We can head to the microscope.
3D alchemy.
To start the process of analyzing the dispersibility of the particles, we will need to first prepare the samples. Preparing the samples is done in our case inside of a mixing cup. And for that, we're going to add some of the ceramic powder. And we're aiming here for approximately 5 to a maximum of 10% in weight. The reason for this is if we have a dispersion which is too dense, we will not have enough of the light penetrating through, and we won't be able to see much under the microscope. So after adding the powder, we would add the liquid or the dispersing medium. In our case, we're preparing an aqueous suspension. Therefore, the medium is going to be just distilled water. And here you can see that I'm preparing the suspension on a weight basis. This is why we're using the balance. And we have the concentrations noted down in grams. So once we have the right amounts, we can close the lid. And we can then take a trip to the centrifugal mixer. So now that we have our sample inside of the mixing cup, we have to know the weight so that we can balance the rotating weight inside of the machine. And then we would add the cup to the mixer, adjust the weight accordingly. Maybe you can check this out and see if it's possible, I don't know. But we will need to adjust the weight so that it balances the weight of the cup. And then we're ready to mix. And this adjustment step is basically to avoid any large vibrations during mixing. Once we're ready, we can set the speed of mixing, whether we want vacuum or not, and the time of mixing. Once we have these 3 parameters set, we can start the mix. And as you can hear or see, the vibrations in the machine are rather low because we were able to balance the weight according to the weight of the cup and the sample inside. Now that we finished mixing, we need to open the centrifugal mixer, take our sample out, and then prepare the sample for the microscope. That's our sample. And now that we have mixed our suspension, we can prepare the microscope slide. And note, whenever you're trying to open a cup after centrifugal mixing, that it might pop out. So try to make sure that you're safely opening it so that you avoid any of the suspension basically splashing on your face. So now we need to prepare our microscope slide. For that, we need the slide itself. We also need a cover glass, which is basically a very thin sheet of glass that would cover the sample, and it prevents the sample from drying out so fast, or you would avoid also the sample touching the tip of the objective. Once we have all the tools ready, we would place a very small sample of the suspension on the microscope slide, making sure not to add too much to avoid your sample from overflowing. And then slowly we would add the cover glass while trying to avoid any entrapped air bubbles. And this way, we would have a perfect sample ready for microscopic analysis. So to check our sample under the microscope, we would need to place it on the microscope table, select the smallest objective or the smallest magnification, and then we would try to find an interesting location in the sample, a place where we can find a representative pattern or the sample of interest. And then we would try to rotate the focus knob to find the sharpest image or the best focus. Usually microscopes have two knobs. One of them is the coarse adjustment knob, and another is the finer adjustment knob. We would start with the coarse one, of course, and then we would move to the finer adjustment knob. Once we have found a decent focus and the sample of interest, we can either analyze it in this magnification, or if more detail is needed, we could increase the magnification by selecting the next largest objective. And in this case, we will have to check again, because usually when we change to another objective, we would need to set the focus one more time. However, it's worth noting that whenever we change to a larger magnification objective, we usually just need to make the fine adjustment for the focus. We will not need to go back and make any coarse adjustments at this point. And before we move on to the largest magnification, I here would like to show you the difference between an agglomerate and the primary particle. And as you can see here on the screen, agglomerates are basically large islands of ceramic particles. They are stuck together by different forces, by different interparticle forces, and they would need a lot of energy to break these particles apart. And between those particles, you can see some smaller particles, which are basically either smaller agglomerates or really well-dispersed primary particles. So if you want to zoom in and see a single agglomerate, to see more of the texture, to see more of the size distribution of these particles, you would go up to the next largest magnification. And in this case, of course, you will have to adjust the focus again. So many times, especially in relatively old devices, old microscopes, the image we see under the eyepiece is actually much more informative than what the camera can capture. This actually makes it difficult for a scientist to record their findings, because what they see in the lab is not exactly what they can show other people, but still the main features of a sample can be recorded in a picture. And here, as you can see on the screen, many of the particles are in their primary state, meaning that they are well dispersed, single particles. But if we move to another location in the sample, you would see more of these much larger islands of agglomerates between the primary particles. As you can see here, the darker colored zones or patches are basically agglomerates of very tiny particles. All right, so now that we have seen our badly dispersed sample, we can try to fix it by adding some dispersant, which is a polymeric additive. And when we do that, we should be able to see better dispersion quality, and a different distribution of particles under the microscope. Let's give it a try. So right now we're gonna try to add a dispersant, which, as I said before, is a polymer. It's an additive. Many of these additives come in a liquid form. Some of them are in the powder form. And for the one we are using today, we will need a pipette. We're gonna use the pipette in order to add a few drops of this additive to our suspension. In this case, we've worked with this additive before, so we know exactly how much to add. But many times we need a balance or a fine digital equipment to weigh the exact amount we need of this additive to get the optimum dispersion. All right. In this case, we're going to add the needed amount of this dispersant. And then mix it again, of course, to allow the dispersant to cover the surfaces of these particles and kickstart its function, which is to disperse those particles and keep them apart. So let's mix it. So now again, we have to place our sample in the vacuum centrifugal mixer, close the lid, and start. Now that we're done mixing, we can remove our sample and prepare another microscope slide. Once again, we will need to add a very small amount of the suspension onto the microscope slide, and of course, cover it with a cover glass. There we go. And now, we can head to the microscope. So now, the same procedure. We place our sample under the light. Can we adjust the focus until we see an interesting location in the sample. As you can see right now, this is the same magnification that we had before. It's a low magnification, and we're not seeing any of the agglomerates which we saw before, basically these large patches or islands, because the suspension is almost homogeneous. It is nicely dispersed, and we can only see primary particles or well-dispersed particles. The problem with this state is that these primary particles are so large in number that they basically block most of the light, and you can barely distinguish between single particles. And knowing that these particles are so small in size, it's even more difficult to see them now under this visible light microscope. And for that, we might need to use an SEM, or a scanning electron micrograph, to see these smaller sized particles and try to analyze their structure, or try to analyze their morphology. That's better. And now if I try to increase the magnification, you might be able to see the single particles under the microscope and the eyepiece, but it's quite difficult for you to see them on the camera. And you'll be able to see basically a full field of very small particles moving because of Brownian motion. And so far, this is a good indication. It's actually enough for you to see that you were able to disperse those particles, because at least you don't have any of these large patches or these large islands anymore. So in this case, you would know that your job is done. You were able to reach a good dispersion. Of course, we take a picture to document the work and save it with the appropriate name. So even comparing this low magnification image would show us that we have a remarkable improvement in the dispersion quality. Almost no agglomerates are seen. We might be able to see small agglomerates here or aggregates, but still, for the most part, it's well dispersed. So after this analysis, you have an idea of how to analyze the dispersion quality of these ceramic particles in a suspension. There are different methods, of course, to quantify and characterize the dispersion quality of particles in a suspension, whether it's an aqueous suspension or resin for 3D printing, for example. And these methods include rheology or other UV-vis spectrophotometry methods or different other techniques. For today, we're gonna wrap things up and say that we see each other next time, and hopefully with another even more interesting method to analyze ceramics.